All right, well, welcome to the last day of vector calculus. We made it. It's kind of crazy how fast it went, but how long it's been. This is definitely one of the weirdest years ever. But yeah, so we made it to the end. So we just have a few things to wrap up and then we can call it good. So first, I want to talk about the quiz that you guys just took, the most recent one, quiz number 5, because there were a few things that we need to address. So the first one went pretty well since it was already parameterized. We saw what we needed to do. We could just take the partials with respect to u and v and then cross them and everything. And that area, I believe, ended up being 4 pi times a. But we definitely need to talk about number 2. So let me go ahead and pull up a whiteboard here and we'll take a look at that. All right, so for this one, we are going to rotate the curve z equals y squared plus 1, and we're going to rotate it about the y-axis. Pen is doing that thing again. All right, so my suggestion with these is always just start with a real quick picture. So we've got z equals y squared plus 1. Here's our z and our y. And we're going to rotate it about the y-axis. So we're going to do that. All right, so this tells me that I'm going to want cross sections that are circles, and those cross sections are in the xz plane. So I can immediately go to, I need my x to be some sort of r cosine theta. My y is going to be whatever it is, and then my z needs to be an r sine theta. My y, since that's just on its own, I'll leave that as just y. All right, so I need to have this sort of structure for my parameterization. Now, you notice I didn't put u's and v's. I usually put that in next, but this is just giving me the structure of what I need it to look like. Okay, so let's actually start parameterizing it with u's and v's and stuff. So for the y, I'm just going to let that one be u. So now if you think about these circles, their radius is actually defined by the z value, right? That right there, that green, that's our radius, which is equal to the z, and the z is y squared plus 1. So what I'm going to do here for my x is I'm going to make this u squared plus 1 times the cosine of v. Right? So the radius, it's the z. The z is y squared plus 1, and the y I'm calling u, so I just have to change that. So then that makes my z u squared plus 1 sine of v. And the cosine sine, you can swap those all you want. It doesn't really matter. You just need to make sure you have one with cosine and one with sine to give you that circular cross section. All right, now I didn't take points off for this next thing, but it's supremely important that we do have this when we parameterize. We need to let be known what our bounds are on the u and the v. Just like when you parameterize curves, you had to put your bounds on t, right? You had to say the t values. And so this actually requires 2. And I highly recommend, I'm not a huge fan of the, I know some of you did something like this. I'm not a huge fan of this one because it doesn't explicitly state which one's u, which one's v. It's kind of assuming you know that u is this first guy. What I would prefer seeing is basically just your set of inequalities telling you what the restrictions are on U and V. But you definitely need these, because otherwise you don't necessarily know which portion of this surface, because this surface is actually much bigger than what we're looking at. And so you don't necessarily know which portion you're dealing with. So make sure you include those. I'm just saying this for like going forward, like on a final exam, for example. Make sure when you parameterize a surface that you include the restrictions on those parameters. All right, so there was number 2. Any questions on that one?
Why did you choose 2? Was there something else added in the question?
I believe that that was part of the question. It said that the y's were between 0 and 2.
Okay.
So, all right. So cool for that. All right. So then number 3, I'm going to go ahead and work all the way through number 3. Most of you did it just fine, but I want to remind you about how to do these integrals. So we're doing a surface integral, and we're integrating, I believe it was y plus 5 ds. And so we have here that r is equal to u v 2v. So we need to go ahead and get the partials so that we can find RU cross RV, and RU cross RV is 0, -2, 1. And we do this because we need the magnitude of this guy. Remember, that's the Jacobian for when we go from the rectangular surface area to the U and V surface area. So this integral then becomes the integral of v plus 5 times the square root of 5. And then this is going to be du dv. Now, we were also told that the u's go from 0 to 1 and the v's go from 0 to 2. So it's really important that you put this Jacobian in. Now, there have been lots of double integral surface integrals where we don't include that, but those are ones where we're not just integrating a function, we're actually doing like a vector integral, like we're finding flux. And when you do flux, you just need to take f and dot it with RU cross RV. You don't actually need its magnitude, but you need the magnitude if it's not a vector surface integral, if it's just a regular old surface integral. All right, so this one then is a real quick, easy, ends up being 12 root 5 once you integrate. Okay, so that was number 3, and that's opposed to number 4. And with number 4, we're actually doing the integral of f dotted with ds. And so notice that this is different now. This is a field dotted with the little area chunk. So this is a flux integral. So we really do need to now take our field and we need to dot it with the normal vector. So we kind of ran into this. You may remember when we were doing last time the Stokes theorem. We're looking at the line integral around the triangle, and we use the normal vector to the plane. And remember, Bradley, you asked me, well, why is it the normal vector? And that's just because that's standard, right? We need a vector that's normal to the surface so we can find out what portion is actually passing perpendicularly through the surface. And for a plane, it's really easy. For something that's not a plane, like in this case, we need to approach it slightly differently. So what you want to do here is, actually, hold on a second. Let me just erase this line for a second. try to give myself a little more space here. Okay, so in this case, we had a surface that was z equals 1 minus x squared minus y squared. And if you want to find that normal vector that we're going to dot with this time, since it's a function, z equals, we saw that the easy way to get that is to build it this way. So we have negative partial with respect to x, negative partial with respect to y, and then 1. And this is for if it's upward. If you want downward, it's actually super easy because you just change the signs. All right, so depending upon which way you've got your surface oriented, you just pick the proper one. So we wanted one that was oriented upward. So we're going to use this guy. So if you take those partials, this vector ends up being 2x, 2y, 1. So that's what you can do if you don't have a plane. Planes are just easy, right? Planes are really easy to find their normal vectors. But let me show you that the same thing would have spilled out if we had done it like with that example from last class. We had this plane, x plus y plus z equals 1. And so we ended up seeing that the vector was 1, 1, 1, right? Just read the coefficients. Well, check out what happens if we solve this for z. You get z is equal to negative x minus y plus 1. So if we do the same structure of the negative partial of fx, well, the partial fx is negative 1. Negative negative 1 is 1. Partial with respect to y is negative 1. Negative that is 1. And so you notice that this formula gave us that same normal vector. So really, we are just using the fact that it was a plane to quickly get our normal vector. Anyway, I just wanted to follow back on that because I think it was Bradley, you asked me that question, and I kind of felt after the fact that we didn't really resolve it very well. So hopefully that makes a little more sense.
Definitely. It also just made me think in physics, we always look at the area vector with respect to whatever we're looking at. Like, is it orthogonal? Is it in the same direction, you know?
Mm-hmm.
Is that the same thing we're kind of doing here? Is the area vector a normal vector with respect to whatever we're looking at?
So I don't know what you mean by the area vector. What do you mean by that?
You know, I don't really know how to explain it.
Because I don't think of areas as vectors, right? Areas are scalars. We could assign some sort of a vector to an area. And so I could totally see that you guys do that. My guess is that if you do assign a vector to an area, it is an orthogonal vector. And its magnitude is probably the size of the area. What's the context? Like, what are you using that for in physics? Like which thing? Somebody's put in the chat board. Hold on.
Yeah, what Victor just said. Like
Okay, so calculating electric flux. Okay, so then that must be exactly the same thing, like what I'm describing. That when you talk about the area vector, it's one that's orthogonal to whatever the surface is. Because if you're going to calculate electric flux, you're doing exactly this. That's what a surface integral does, is it calculates flux. Your big F is just the electric field, right? And then, so let's see. So Victor, you said integral of an electric field times dA, or so dotted with dA. Okay, so yeah, so we've been calling it ds. You guys are calling it in physics dA. It's the same idea. So I guess my long story or long answer short, Bradley, is yep. It's exactly the same thing. You're just doing flux integrals. All right, so if we now do this calculation, right, this is going to end up being a double integral of 2x squared plus 2y squared plus z. We can replace the z because we have the equation for it, right? If we come back down here, we had z is equal to 1 minus x squared minus y squared. So this ends up being the double integral of 1 plus x squared plus y squared dA. But now we need to tackle this region. And if you look at what this was the surface 1 minus x squared minus y squared, where z was greater than or equal to 0. Yeah, for this one was 0. So if you think about what this looks like when we're at z equals 0, it's a circle of radius 1, which means we want to use polar. So if we convert this to polar, we're going to get 1 plus r squared times r d theta. And then our r's go from 0 to 1, and our thetas go from 0 to 2 pi. All right, so you do this calculation, you get 3 pi over 2. All right, so this is the process for doing your surface integral. In this case, I didn't actually do a parameterization for the surface. I left it as z equals, and you can always do that if you've got a function. But the other thing that I need to bring up on this, because quite a few of you did this, a lot of you use the divergence theorem here. And the problem is the divergence theorem does not apply here. This is not a closed surface. This doesn't actually have that bottom on it, right? It's like this. So we've got a bowl. I happen to have one here, right? This is my surface. You notice there is nothing here, right? This is my surface. So I'm finding the flux through this. And because it's not closed, I cannot use the divergence theorem. However, if I were to cut out a circle and put it on the bottom here, so pretend that my hand is that bottom surface, then I can use the divergence theorem, right? So I think we did an example. There was a homework question that somebody asked about either last time or the time before, where we did it over the entirety and then took away this one. You could do it that way. If you were to do the divergence theorem and then figure out what the flux is on the bottom and take that away, that's actually okay. That would work out. But as it is, we can't use the divergence theorem. So some of you will notice that, like, if you look at your comments, I gave you a grade, and then all of a sudden I posted something else because I caught that it turns out that if you do the divergence theorem, you get exactly the same number because the bottom surface has a flux of 0. So I didn't actually catch that at first. So for some of you, I had to go back and find that. So that's when you go, dang it, how come he had to figure that out? But alternatively, we could have done that. We could have done a divergence theorem and then figure out what the flux is on that bottom surface. And the flux on that bottom surface would have been really easy to do because you think about that bottom surface, it's the xy plane, or the circle in the xy plane. Its vector that's going to be pointing down is 0, 0, minus 1. And so if we were going to do it that way, let me actually show you because I can just mark this up here real quick. Let me just clear some space. So suppose we had decided to look at what the flux is through the bottom surface. So we're going to be integrating x, y, z dotted with 0, 0, minus 1. And it's 0, 0, minus 1 because it has to be pointing outward. And if we've got that bowl with the bottom, that bottom vector is pointing down, right? So this is saying we're doing the double integral of negative z. Actually, that should be a dA. Well, think about the bottom surface. The bottom surface is z equals 0. So that guy ends up equaling 0. So knowing that actually tells us then if we use the divergence theorem will give us the exact same value. So just FYI. All right, so okay for number 4. But it brings up some important things. With the divergence theorem, make sure it's closed. If it's not closed, you can make it closed, but then take it away. Also, if your surface is a function, build the normal vector using negative fx, negative fy 1. Way faster, right? And then just the general process is here too. All right, so any questions on the quiz? Other questions on the quiz? All right, well then I'm going to stop sharing that. Excuse me. So then what about homework?
I have 2 questions, not necessarily on the homework, just
Okay.
about the homework.
Sure.
So, what do you recommend on Stokes' theorem? Like, if you want to use either the double integral of the curl of f or the line integral, do you look at the parameterization or the bounds?
Okay, so all right, so here's what I look at. First, for the line integral, I look and see, is that curve in a plane? Okay, is that curve actually fit in a plane or not? Because if it fits in a plane, I probably am going to want to do the double integral, the surface integral. Because if it fits in a plane, it's really easy to get the normal vector. And I can use any surface, right? Kind of the key to Stokes' theorem is that you can use any of the surfaces with that boundary curve. So if it's in a plane, I'm just going to pick the surface that's in that plane. So that's one of the things I look at is I just look and see, is that curve in a plane or not? Something else I look at is I look at how easy is it to parameterize the curve. Because if the curve is really easy to parameterize, like a circle, that definitely suggests line integral. If it's not easy to parameterize, then I probably want to do the double integral. I want to do a surface integral. Hopefully, that's going to be such that the surface itself is easily parameterizable, if you want to call that a word. So that's something else I take into consideration. Sometimes I actually look and see what the curl of f is. Because if the curl of f is nice, right? Like if it ends up being a really simple vector, then when I end up going and putting that into the surface integral form, and dotting it with the n, that double integral ends up being a piece of cake. Like especially if it ends up being a constant, because then it's just going to be that multiple of the surface area. So if we're dealing with the surface whose surface area is known, like a cone or a sphere or something like that, that can be really fast too. So there are lots of things that I look at, honestly, when it comes down to which one am I going to do. And sometimes what it is I start doing it with one side and I realize that it's getting big and ugly and nasty. And then I stop and I go, okay, what about the other way? Right? So the line integral, oh my God, this is horrible. Let me check the flux real quick. Or vice versa. Anyway, is that kind of what you were looking for?
Yeah, definitely.
Okay. All right. Well, while I was talking about that, Ralph just put a couple in the chat box. He said he'd like to look at numbers 6 and 7 from 6.8. So I'm going to go ahead and take us over there, and we'll take a look at it. All right. Let me switch my screen. And I apologize. Things are definitely a little slower today. For those of you who didn't know, I had a meeting right before this one that went exactly up to 1 o'clock, so I didn't have time to get things up like normally I have your Canvas shell up and ready and whatnot. So just bear with me here. All right, well, I guess that means that this is our last chance for any terribly good, bad jokes. Anybody have any while I'm pulling this thing up?
What does a mathematician say when he gets mad? Or a physicist, either one.
Ooh, or a physicist.
Yeah.
I don't know, Jacob. What does a mathematician / physicist say when he gets mad?
What the flux? Yeah, it's really bad.
No, but that's exactly my kind of bad joke. I love it. So I guess that's what the WTF means.
Yeah, what the flux?
So so pretty much now on any homework problem where you have to calculate flux, I can just write WTF, and then we all know what it means.
Yeah, do that on the exam.
Yeah, right. That'll be a good one. That'll be a good one to explain to like my vice president or something when she's like, so why are you writing WTF on all your exams? Anyway, all right. So Bradley, you got another joke?
Yeah, what do you call a rude acid?
A rude
acid.
What? A rude acid.
I get it.
What do you call a rude acid?
Amino acid.
But a bump.
Yeah, there it is.
There you go. Amino acid. All right, I love it.
I kind of wish I was in Sean's class or.
Yeah, I was about to say.
He did ask us bad chemistry jokes, and I just learned that one, and I couldn't tell him.
Oh man. All right, no, but yeah, that's perfect for chemistry / bio. All right, cool. So we now have delayed enough. Thank you for that, guys. I appreciate always getting. Oh, are you kidding me? I always appreciate getting really bad jokes to add to my repertoire. Oh, speaking of, so today in first year calculus, we've been doing, we finally got to antiderivatives. And so I shared them what do you get when you integrate 1 over cabin, d cabin? You guys know that one?
I feel like we should.
I might have shared that with you guys. Maybe I didn't. Okay, real quick, hold on. It's the last day. What do I care? We can. So this is my second favorite math joke of all time. The first favorite, of course, is what did 0 say to 8? But so what do you get when you integrate 1 over cabin, d cabin? Anybody see it?
Log cabin.
Okay, so log cabin. That's not quite right, actually.
That'd be natural log of cabin.
A natural log cabin?
Oh, there we go.
Well, you're getting closer. That's still not right. But what you get when you integrate 1 over cabin d cabin is a houseboat.
I don't get it.
It's because you forgot the C.
Oh my
Man,
gosh.
fuck.
All right, so there's your. That's a dad math joke if I've ever heard one. Right?
Oh yeah.
So,
Absolutely.
because most people, what was funny is one of the guys in class. As soon as I wrote 1 over cabin d cabin, he went, "Oh, ha, 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 a log cabin." I was like, "Well, you're close." So, but yeah, 1 over cabin d cabin. Anyway, all right. So let's get back to actually doing some math. Oh shit!
No, let's just tell math jokes until the exam.
Maybe that should be the exam. I'll just give you like
best math joke. Yeah.
a whole bunch of math jokes, and you have to answer them, and whoever gets the most of them right. No, all right, so let's take a look at this guy. I kind of feel like, didn't we do this one the other day?
One very similar.
I think we might have done this exact one. What's number 7 look like? Okay, so number 7 is actually really similar. So maybe we'll do that one because that's definitely different. Oh, we did number 5. Okay. All right. Well, so 6 is going to be a similar setup, right? We've got all right, so we've got this field. Let's not worry about the field just yet. Let's look at the surface and let's figure out what that surface is so that we can try to visualize it and see if it's closed or not. If it's not closed, we'll make it closed so we can make use of the divergence theorem and whatnot. So I'm just writing this down really quickly, because I'm going to go to the whiteboard and I don't want to have to keep bouncing back and forth. All right. So let's go to the whiteboard and let's see if we can bang this guy out.
Real quick, I just thought of something.
Sure.
You know what blows my mind?
What's that?
Is that the applications between differentiation and integration are so different, yet they're almost the same thing.
I know, isn't that crazy? Like, you think about how you were first taught about integration and you know that it's areas, and differentiation, it's slopes of lines. And it's like, oh my God, they're completely different, and yet they're two sides of the same thing. Anyway, should I pull a Giuliani? Now I blew my nose, start wiping my face. All right, so here is that surface. But oh, by the way, Bradley, I appreciate you bringing that up. I think that's one of the most intriguing things about math is when you start seeing all these connections to seemingly random things. And we've actually seen a lot of that in this last week or two in this class, right?
Yeah, with like the theorems and connecting like various things that were unconnected before together.
Yeah, like you can get a line integral by using a surface integral. What? Or a surface integral by using a triple integral, or it's kind of crazy. All right, well, let's first start by looking at this. And what kind of shape is this? Can you figure out, see what that is?
Isn't it a paraboloid?
It is not a paraboloid. It would be a paraboloid if there was no square here. Right,
Ellipsoid?
All right, so it would be an ellipsoid if that was a plus and equals something else. If we put it into the form that you saw when you learned about quadric surfaces, it would look like this. Does that help anybody out? Because again, ellipsoid would have been if that was plus.
Now I'm thinking cone.
Yeah, it totally is a cone because it equals 0. All right, so this is a cone. It's oriented with the y-axis going down the middle of it. Actually, y equals 12 going down the middle of it. So it's oriented in the y direction. So it's a cone. And in terms of what it looks like, let me do it this way. I'm going to do this be the y-axis. And so the xy plane is down here. I'll just do this as the x-axis. So we're going to see a cross section of it. All right. There's a tip up here at y equals 12 is where the point of this cone is. Right? If you plug in 12, 12 minus 12 is 0. So you get 16x squared plus 9c squared equals 0. So you need an ellipse of radius 0, basically. Okay, so then if we come down here where y is equal to 0, you're going to get 16x squared plus 9z squared minus 144 equals 0. And I just wrote xy, I meant xz. So I don't know if you remember this term, we call this a trace. That's the trace of that surface. But if you let y equal 0, you get this. This is definitely an ellipse. And if I rewrite it in the form that you know, it looks like that. So what we're getting is the cone that does this. But the base of it is not a circle. The base of it's actually an ellipse. All right, so how are we with the surface? Are we visualizing it? Do you see what's going on? Are we all right with that part? All right, so now let's think about this. In terms of the divergence theorem, as it is, we cannot do it. The divergence theorem is not going to apply because just like that one on the homework or on the quiz, this is not closed. All we're talking about is the cone. But we can close it off by putting that elliptical disk that lives in the xz plane. Right? We can put that in there. So if we were to close it, then the divergence theorem, so if we do divergence of f, it's going to be the surface integral of the cone plus the surface integral of the disk. So if I want the cone, I'm going to do the divergence integral minus the surface area of the disk. All right, so let's see how easy those are to do. All right, so how about we calculate the divergence of f? If we go back to mine, the field was x squared z 3 minus 4xyz xz squared. So the divergence of that is going to be 2xz minus 4xz plus 2xz. So that was the partial of the first one with respect to x, the second one with respect to y, the third one with respect to z, which is 0. hot damn. The divergence is 0. In fact, since this divergence is 0, it's always 0. That means it's a source-free field, which means anytime you have a closed surface, you're going to end up with 0 flux. All right, so basically that just means that the cone and the disk are going to have opposite fluxes. All right, so let's find the flux through this surface. All right, well, we need a normal vector. So we need the normal vector that points this way. What's that vector going to be? What are the components of this one?
1, -1, 1.
Not quite.
0, -1, 0.
There you go. So it's going to be 0, -1, 0, because it's just pointing straight down. Okay, so for that, so I guess we're doing the integral of the disk. All right, so it's going to be the double integral of the field dotted with 0, -1, 0, which gives us, if we come back and we dot with this guy, we're going to get 0. Then we're going to get -3 plus 4xyz plus 0. All right, so there's our F dotted with that guy. But here's where we're going to make use of the fact that we know where this ellipse is. That ellipse is in the xz plane, right? And so what do you know about the xz plane in terms of the letters x, y, and z?
Y is equal to 0.
Yep. So this guy right here, that guy's 0. Which means this one's just -3 dA, which means it's going to be -3 times the area. And it's an ellipse. I don't know if you remember the formula for the area of an ellipse, but we have actually generated it this term. But for this one, it's going to be 12 pi. Do you remember where that comes from?
Yeah, isn't the 2 radii times
Yep.
pi?
Exactly. It's pi times a times b. All right, so that's -36 pi. So the disk has a flux of -36 pi. So what's the flux through the cone then?
36 pi.
It's positive 36 pi. So minus -36. All right, so there's an example of where the divergence theorem can actually be pretty quick. I don't know if it's actually better or not than just doing the integral at the start. Because this actually can be written as a function, right? We could actually solve this for y, get it as y equals instead of z equals, because we're doing it, we've got it oriented differently. But we could get it as y equals, which means we don't have to parameterize. We can just go straight to our n, and we can get our n using that negative fx, negative fy, comma 1, except in this case, it's going to be negative fx, comma 1, comma negative fz, because we've got x and z as our variables. And then we'd have to dot it with the original f, and that's where it might get nasty, because when we replace this y with what the function is and everything, that could get pretty ugly. The bounds on x and z are going to be the bounds for the ellipse. So we'd probably want to do that to go to polar. So that one, it's doable, but it's probably going to be more work than what we did just right here. So in a pinch, you can always do that. You can go ahead and close your surface and then use divergence theorem. Okay, so this is a lot like number 5, except I think number 5, maybe we had a hemisphere on top, but it's really the same kind of approach. All right, so is that good for number 6 there? Yeah. Okay, so then let's go take a look at number 7. And I remember number 7 had something about a tetrahedron. Okay, so T is a tetrahedron with vertices at the origin and at 3, 0, 0, 0, 2, 0, and 0, 0, 2. A fluid flows with this velocity. So that's our field. Position is measured in meters. Speed is measured in meters per second. Okay. Find the rate of flow outward through the slant surface of the tetrahedron, but only face it's not parallel to any of the coordinate planes. All right, and then it says, hint, using the divergence theorem, the problem can be done with geometry only and not evaluating any integrals. Ooh, I like that idea. All right, so let me go ahead and write down this information again. And let's see what we see.
I'm curious as if you do it differently than how the internet told me how to do it.
Probably. I tend to find that I don't think a lot like the internet. I don't know. You guys know me well enough that you know that what's up in here is a weird place, right? Like, I don't exactly view the world the same way as the rest of the world. So,
Craft root beer, baseball, and math that I could never comprehend.
yeah, false. You could comprehend it. But yeah, I think it is the intermixing of all those things that make me pretty unique. All right, well, let's jump to this. I'm going to start by drawing a picture to help us see the tetrahedron. I'll put a couple of tick marks on here. Okay, so on the z-axis, we've got a point 0, 0, 2. On the y-axis, we have a point 0, 2, 0. And on the x-axis, we've got the point 3, 0, 0. Okay, so I'm going to go ahead and draw all the edges of our tetrahedron. So I did draw along the axes there, but those are kind of showing you the back sides. So tetrahedron has 4 surfaces. They're all triangular. So we've got this triangle that we're kind of looking at. Remember, this is the slanted against the corner of the wall. And then the other 3 are triangles that are on the 3 sides of the wall. So the floor, the window side of the wall, and the whiteboard side of the wall, like we did in class before. All right, so that's what this thing looks like. So now let's start talking about flux and all that good stuff. So we definitely can use the divergence theorem here because it is closed. So let's go ahead and get the said divergence. So the field is this guy. So the divergence of F is going to be e to the y plus 1 minus e to the y. Oops, I should not have put bracket there because divergence is a scalar. And if we add those all together, that equals 1. Okay, that just made my day. Why did that make my day?
Because now it's just the area of the tetrahedron.
Okay, it's actually the volume. Yeah, but yeah, so
Oh,
it's the
volume,
volume, right? So when I go to the divergence over this region, okay, well, if I'm triple integraling 1, all right, so that side of the divergence theorem is the volume of the tetrahedron. Awesome. All right, so now let's look at the surface integrals. I actually have to do this in 4 pieces, right? So if we're going to do, here's the other side. I'm going to break it into 4. Okay, and I'm not going to write what's in here. I'm just going to describe where we're going to look. So we're going to look at the ones that are planar. So the one in the XY plane plus the one in the YZ plane plus the one in the XZ plane plus the one that's slanted. Okay, so let's look at these ones that are in the planes. So for the one in the XY plane, that's the triangle, X, Y, Z. So that's the triangle that's on the bottom. All right, so in terms of its normal vector, what normal vector are we going to use there?
0, 0, negative z, or
Okay,
-1.
There you go. So 0, 0, -1. So when I do the dot, this is going to be x e to the y, comma, minus z e to the y, dotted with 0, 0, -1, right? And look at what's left in there. It's just z e to the y. All right, so we can do the same thing for the YZ plane. The YZ plane, that's the one that's on the back end. And for that guy, we want to use -1, 0, 0. So I think what I'm going to do, because I'm kind of running out of space, I'm just going to write our ends up here. So if n is -1, 0, 0, and I dot that with f, I get negative x e to the y. Okay, so then the xz plane, that's the one that's over here on the left. We're going to want the vector 0, -1, 0, which then when I dot it with my original field just gives me -y. Oh man, that's going to be an easy one to integrate. All right, so far so good. Now, they told us that we don't actually have to calculate any integrals, but we still have some integrals down here. Why is it that we don't actually have to calculate these? Does anybody see it? Let's go back to the XY plane. What's the equation of the XY plane?
Z equals 0.
Yeah.
All right, so z equals 0, right? XY plane tells me z equals 0, which means I'm integrating 0. Yeah,
Oh, that ends up being 0, and then
bitchin'. Okay, so now go to the YZ plane. Well, the YZ plane, that's x equals 0. Well, if x equals 0 here, what does that integral give me?
0.
0. XZ plane, y equals 0. 0.
whatever variable is missing is the 0.
Exactly. Okay, so let's think about where we are now. We've gotten ourselves to a point where we see the triple integral gave us the volume of the tetrahedron. The surface integral, when I added them all up, 0 plus 0 plus 0, blah, blah, this is the, well, actually, let me just do it this way. This is the flux through the slanted side. All right, so all we got to do is get the volume of a tetrahedron. And that formula is actually known. Anybody know it? I'm just curious.
Isn't it a squared over 6? Something like that? Like the side squared over 6?
Something like that.
Yeah. Did you divide by 6 for sure?
Yeah. So this is really easy to, I mean, you can do a Google search for it or whatever, right? Just go to Google and do volume of a tetrahedron. But what it ends up being with the formula is you take the, well, all right, it depends if it's regular or not. If it's regular, this one's not regular. Regular would mean that all the sides are exactly the same length. You take that length, you cube it, and you divide by 6 root 2, obviously, right? But it's actually equal to 1/6 the triple product. Do you guys remember triple product?
That's what I did. I crossed the first 2 vertices, dotted the third, and then divided by 6.
Yeah. So the triple product, that's the U dotted with V cross W. We did that not that long ago when we were doing surface integrals, right? So in this case, then, we need to go ahead and create those sides, right? So the volume for this one, well, here are the vectors on our sides. There's 0, 0, 3, no, 0, 0, 2, 0, 2, 0, and 3, 0, 0, right? So the easiest way to do the triple product is just to put these 3 into a matrix and find its determinant. I'm going to put it in like this. I'm going to put them in that order for a reason. And this is a fact you may not know about determinants of 3 by 3 matrices or determinants of matrices, period. You will learn about this next quarter in linear algebra. But if you want the determinant of this, since it's a diagonal matrix, since there are only elements in the diagonal, its determinant is just the product of those guys down the diagonal. So that's 12.
I think that's the easiest cross product we've ever done.
Yeah, quite possibly. So that's 12. So the volume of that tetrahedron is 1/6 of that, which is 2. So the flux through the slanted side of that tetrahedron, it's 2. And notice that we didn't do a single integral. I mean, I set up a bunch. I know when you're actually looking at that whiteboard and you see all that garbage, right? I mean, but we didn't actually end up having to calculate any integrals. And that's really because the form of these functions, after we did the dot products with those in those planes, they left us behind the variables that ended up being 0. So when you have coordinate planes, those tend to be kind of nice. They simplify things down a lot. And we even saw that. Go back and look at the problem we did prior to this, number 6, the one with that elliptic cone and whatnot. And we had to find the flux through the surface, the disk that we introduced. That disk was in the XZ plane, I think it was. But the fact that it was in a coordinate plane made it really easy to calculate for 2 reasons, right? One, n is easy to find, right? Look at the n's that we needed for those surface integrals. -1, 0, 0, please. I'll dot with that all day long, right? So that happens, plus one of the letters goes to 0, right? So if you can get surfaces on a plane, on a coordinate plane, do it. Do it, because the surface integrals end up being really easy. All right, so better for number 7 here. Okay, so Victor, you said, so you found the equation of the plane and then found the flux. Okay, yeah, so, and that's the alternative, right? Is just to do the surface integral itself. So you find the equation of that plane and then go through it. So in terms of the bounds, that one, think of it, I would solve it for z, get it as z equals, so that then we can do that trick with the partials, right? Which is the same as finding the normal vector and then scaling it appropriately. But then in terms of the bounds, it's going to be a triangular region. It's going to be the triangular region. If you come back and you look at this picture over here, it's that base triangle. So you'd want to do integration man. I'd probably go with the y equals first from 0 to whatever this line is. And then the x's are going to go from 0 to 3. I think that this is one where I wouldn't use the divergence theorem if all I was looking for was the flux through that slanted side. I would just go ahead and do it because it's a plane. Planes are really easy to find equations for. They're really easy to find normal vectors for. And seeing that the region over which that plane is lying in the xy plane is a triangle, that's pretty easy to set up in terms of the bounds. But anyway, I would probably have just brute force this one and done the surface area, but it is kind of cool to see that it turns out that you can actually answer this question without doing a single integral. But it's because it's a nice shape. And that nice shape gives us a nice little formula. Oh, by the way, that formula, where it comes from, you can actually do it with the geometry of the tetrahedron. Basically, you look at the volume of a box, of a parallelepiped, and then you see that there are actually 6 of those tetrahedrons that would fit in it. So anyway, you can do that using vector stuff. All right, so okay for, what was this one? 7, I think. Feeling a little bit better about it? Hopefully you at least see that it's kind of interesting how it all played out. All right, cool. All right, so don't forget that homework stuff is due Monday night at midnight, right? Again, I think it's only the 2 sections, the one on the divergence theorem, which now I've done like half of them for you. You're welcome. And then the bit on Stokes theorem. All right, so let's talk about this final exam. So I was looking at everything, and it looks like everybody's eligible to drop their lowest exam score, and that's assuming that you guys do these last 2 homeworks. So make sure you do these last 2 homeworks so you can drop that lowest exam score. So I went through and I ran the numbers. So I've got those. If you're curious what your specific one is, I'll let you know. We don't have to do that over Zoom here, but so I've got your exact standings, and I also calculated approximately what you're going to need to bump yourself up to the next letter grade, if that's even possible. Because for some people it's not, and for some people it doesn't matter, right? Like if you already have a 90 something, it doesn't matter, right? To bounce yourself up. And then if you're like, let's say you're at an 81%, at this stage of the game, you can't get up to a 90 anyway. But if you're at like an 87, I went ahead and calculated what you needed to bump up to the next grade. So I've got that information as well if you want it.
So we would just email you about that, or?
Yeah, you can just email me. Actually, you know what I think I'll do as I'm talking here is I'll just start sending them to you guys, because I can do individual chat messages. So and I'll go ahead and do that while I'm talking. But the reason that I'm bringing this up is I'm going to make the final optional. Okay, so you don't have to take the final if you don't want to. All right, so.
You know you're a gangster, right?
Of course.
All right.
And of course, I hold on to this until the very last minute because, you know.
You want people to actually be studying for the final so they learn what the content was.
No, it's really because I didn't decide until earlier today that this is what I wanted to do. So anyway, but here's the deal. If you take the final, the result of the final is the result of the final. It could cause your grade to go down. It could cause your grade to go up. It will follow according to how I have everything set up in terms of the grading breakdown. So, it is what it is. If you don't take the final, then you get the grade that you currently have. All right.
Which would be the one you're sending us, correct?
Which is the one that I'm sending you. So, yeah, Bradley, you should have gotten one. Caesar, I just sent Eduardo's. So I'm making my way down the list. Okay, so basically here's the deal. If you're happy with the grade that you've got, or if it's a grade that cannot change in terms of going up, cannot change, you probably, well, if you're happy with your grade, you definitely don't want to take the final. If it cannot be raised, you shouldn't take the final, right? Because if the only possibility is that it actually goes down, if it were me, I wouldn't take that chance. All right, so really the only people that should consider taking the final are those that are either gluttons for punishment, they just, are that way, right? Or those of you that see what you need to get to the next higher level and feel like that's attainable. Okay, so Jordan, I see you keep popping in and out like you're about to say something. Do you have a question or something?
All I'm thinking is, oh, thank God.
Okay. All right. I wasn't sure if you were going to be like, well, what about me? What's my score? I haven't quite got to you on the list yet.
Hey, Bruce. So if we don't need to take the final, do we just email you or?
Yeah, so here's what I'm going to want to do. I'm actually going to want to hear from you either way, whether you want to take it or not. And yeah, just send me an email. You don't have to decide right now. Okay, you take some time, especially if I know some of you, you already know, right? I know some of you already know. So for those of you who do already know, that's cool. You can let me know as soon as you want. If you want to think about it, let me know. Just let me know by Monday, if you would. If you want to take the weekend to decide, that's cool. I'm totally down with that. But yeah, just let me know, because if it turns out that nobody's going to take it, then I'm not going to bother writing it, right? But if you are going to take it, that's cool. That don't think, oh man, now I'm going to make him write a test. It's not a problem. I'm going to write that test if anybody wants to do it. So hopefully you guys all got a message from me in the chat that has your current score. And then I either put cannot raise if it can't be raised, or I put what you needed to raise it to the next higher grade, right? So like if you're at an 87%, then I put 87, and then, like 93 for an A or whatever, right? So that should let all of you guys know kind of where you stand. Now, I also want to make sure that I email people that are not here. I see Seamus disappeared on us, so I'll get this out to him. Let's see. No, Jesus is there. Oh, okay. I got to get this out to Matthew. Okay. So it looks like there are just 3 folks in the class that I need to get this to. Anyway, all right. So that's where we are. So for the remaining of the day, oh, so real quick, Victor, actually, I'll reply to you in chat here. So for the remaining of the day, I'm willing to do whatever. All right. So for those of you who just said, can it get raised or not? You already have an A, right? You're over 90%. If you're over 90%, you already have an A. You can't go higher than an A. So I know it's one of those things you start, wait a minute, I can't get raised. I mean, you could raise it from, the 93 to a 94.
Or you could drop away.
Yeah, or you could drop down. Yeah. Anyway. All right. I forget what I was going to say. Oh yeah. So I'm more than happy, because we've got about 20 more minutes. I'm more than happy to do more review, talk about any of the stuff that we've talked about. Or we can call it a day, or we can just sit here and BS. But if that's what we're going to do, I'm going to turn off the record. All right.
Are there any other things in Stokes' theorem you wanted to share with us, or did you pretty much hit it all?
No, I pretty much hit it all. I was just going to do another example or two, but I think, I don't know, that they're all the same, right? I mean, the process is all the same. It's just a matter of, well, I've got to parameterize this curve a little bit different, or parameterize this surface a little bit differently, or and in terms of some of the ones that you guys asked me about on homeworks, we addressed some of the stuff that was kind of floating out there. Like, I remember last time somebody asked me about the one where the surface was some sort of funky surface, but we ended up doing the surface integral of the planar piece instead. And that's a result of Stokes' theorem. That's another big part of Stokes' theorem, is as long as you've got as long as your surfaces share the same boundary curve, you can, do whichever one. And so always pick the easier one. And in general, the easier one is the planar surface. If you guys haven't caught that yet, that planar surfaces are super easy to do surface integrals for, you haven't been paying attention, because just about every single one of them where we've had a plane, it's been fast, right? It's been super fast and super easy. So that's just some advice from me to you. If in your future math science endeavors, you end up having to do surface integrals, try really hard to get to planar surfaces, right? And one of the ways you can do that is by making use of Stokes' theorem, if possible. Speaking of future classes and stuff, just gonna remind you guys what you should be doing in terms of the math. So I imagine a lot of you have already signed up. If you haven't, realize that you can sign up for both winter and spring quarters now. And so in the math sequence, it will be linear algebra in the winter, and Larry will be teaching that, and then differential equations with me in the spring. Take both of those classes. You really should take both of them. I know they're not all both required by everything. Just about all of you, because I know you're going into like engineering and the like, are going to need differential equations. The linear algebra may be optional, but I'm going to highly recommend that you choose that option, because some of what we do in linear algebra will help you with differential equations.
Is DiffEQ the last possible class we could have with you, or?
It's the last math class. I might be teaching Physics 208, the modern physics, in the spring. That I'm not sure about yet. We haven't figured that out. There are a lot of things up in the air for spring in the physics department. So there's the potential that I'm teaching that. Also, all of you that are taking Physics 207, take Physics 208. Oh, good Lord, don't stop now. Take that last one, because that's where it gets really, really cool. It's also really mathy. So you guys have done so much math that it's probably gonna, like, it won't feel like that big a deal, but we get to talk about some really trippy stuff in there. So again, I don't know if I'll be teaching that, but sign up for Physics 208. But yeah, Jacob, that's the last math class of, like, that's the last thing we offer at this school. You guys are out of math, unless you want to go back and take statistics, which I wouldn't recommend unless you have a program that specifically requires taking our statistics class, just because our stats class is not a real mathematical stats class. And for a lot of you, you're going to have to take a more mathy stats class. Like, just so you know, as a math major, I took a 400 level probability and statistics class, right? Like a senior level class, which doesn't look at all like our school's Math 201, because our school's Math 201 is not designed for math majors and the more, let's call it the mathier of the sciences. You know what I mean, right? So don't take stats. I wouldn't recommend that. You're not going to be getting much out of it. Better to take something else. So Caesar, is Physics 208 a common prereq for most engineering transfers? I don't know the answer to that. I know that it depends on the program you're in. Some engineering programs only require the first 3 quarters. So that'd be like the equivalent of a year. But you should take it for sure, because it's cool. My recommendation for Physics 208, or for taking that, is twofold. One, if you end up needing it, like if you end up deciding on a school that then required that you have it, it's probably better to have it done. Take it here where it's a small class, where, you know, you've got a professor that you can ask the questions and they actually know who you are, right? You're not just a name. You're not just one of 100 people in a classroom. And it's cheaper, right? It's a lot cheaper to take a class here than, say, at Davis or something like that. But also, it's really cool. because what we talk about in that class, you talk about optics. So you talk about light and how light works, which in itself is pretty cool. But then we get to modern physics. So you talk relativity, how people's clocks don't progress at the same time, how we don't all measure lengths the same way, things like that. You get into quantum physics. So how like subatomic stuff works, and there's a lot of really wild trippy stuff in there. Like I know I talked about that one time when we were talking about electrons, right? And how like the electron in your finger might actually be on the moon and whatnot, right? So we talk about that kind of stuff too.
If I ever walk through a wall, Bruce, I'll let you know.
Oh, please God, let me know. And if by any chance you got it on video, I'm gonna definitely want to see that video. So anyway. All right. I forget what I was doing there. I think I was just reminding you, sign up for, don't forget to sign up for classes, right? And you can go ahead and take care of knockout spring at the same time. So in terms of the math sequence, you want to do linear and diffie Qs. I highly recommend both of them because of who you guys are and what you're doing. And then you guys that are in the physics sequence, make sure you continue on, take physics 208. It's sort of like if you were to be watching, the Avengers, like this most recent Avengers movie, and you just stop in the middle and you're like, but what happened? Did they get all the stones? Were they able to turn things back? And you're like, Right.
Speaking of that last Avengers movie, there Tony Stark figures out time travel. Sorry if I just spoiled it for someone, but
oh my God, spoiler alert.
Yeah, what are your thoughts on that?
I'll share that for an off the record discussion
Okay.
at some point. But just real quick, Seamus, you just pop back on. What I'm sending you, I'll get to you in a second, Jordan. What I'm sending you, Seamus, is your current score in the class. Because I don't know if you heard, but I'm making it so that the final exam is optional.
Wow, yeah, Victor sent me a private message. I was like, wait, is he serious? I couldn't, sorry, Victor, I didn't know if you were pulling my leg or not. So
no. Victor's a stand-up dude. He wouldn't do that to you. But anyway, so yeah, so I just sent you your current grade. So decide what you want to do with that. Just realize that the final can make your grade go down.
And do I send you a private message?
You can send me a private message. You can email me.
Okay.
Whatever. Just let me know by Monday.
Okay,
I think
cool.
I already know the answer to yours, but.
Okay, cool.
So Jordan, I saw you raise your hand. You actually like turned your video on. I was like, oh my God, I haven't seen Jordan in forever.
Yeah. Okay, so where would we find the part where you tell us the grade?
Like what I just did right now?
Yeah.
You want to go to chat. Look, there should be a button. If you're on a computer near the bottom of the screen, there should be a thing that says chat. If you click on that, it should give you like a little window of all the chat. And you're muted right now. I can't hear you.
So that's my final grade without taking the exam?
Yes. So
Okay,
that number I gave you, the first number is your current grade with the dropped of exam. And then because you were one of the ones that it's possible to go up, I put next to it what you need to get on the final to bump yourself to the next grade up.
Yeah.
Okay.
Also, talking about time travel, technically time travel to the future is easier than time travel to the past. So all you need to time travel to the future is get near a force of heavy gravity for a long enough time.
You're always time traveling to the future.
Yes.
That is also true.
Yeah.
And that is definitely a bit of relativity that we get to talk about.
Like if you park yourself
Physics
near,
208.
like if you're able to move yourself near a black hole for long enough and then left, it would seem like for you a short amount of time passed. For everybody else, decades, years, or hundreds of years might have passed.
Very true. Or you just got to go fast enough.
Yeah, and then
I
a
like
bunch of
that idea
scientists
too.
who thought of a possibility to travel backwards in time. You know what they called it? They
Nope.
called it TARDIS.
Oh yeah, which is very appropriate.
Yeah.
All right, so I think we're probably good in terms of on the record. So I'm going to go ahead and stop recording.